In 2017, 8 researchers published a paper titled "Attention is All You Need," a publication that would become arguably the most important paper in modern computer science. For years, the consensus was that AI had to process language sequentially, step by step, word by word. But this team challenged that fundamental assumption. They threw out recurrent loops entirely and had showed that processing every token simultaneously in parallel wasn't just faster, it was revolutionary. By replacing slow sequential recurrence with pure self-attention, they unlocked massive GPU parallelism and solved long-range memory loss in one stroke. It proves that all it takes is a small group of people thinking in a fresh direction to change the world. And by breaking down every single line of this architecture today, who knows? The next groundbreaking revelation in AI might just come from someone watching this right now. In this video, we're building a transformer AI completely from scratch in PyTorch, line of code by line of code. Instead of using pre-made libraries or predicting whole words, our model works character by character, reading individual characters to learn how words are built from the ground up. Our goal? Training our model on original Pokemon names until it learns the hidden phonetic rules of Pokemon biology and invents brand new realistic Gen 1 species. We'll cover tokenization, embeddings, scaled dot product attention, multi-head projections, causal masking, and residual blocks. Let me show you how it works. For transformers, sequence modeling relied on recurrent neural networks, or RNNs. The problem with RNNs is, just like the name implies, is everything is recurrent. This means everything has to go one at a time, or in a row. This means that step 50 cannot compute until step 49 has finished. This creates an O of n sequential bottleneck, leaving modern parallel GPU hardware heavily underutilized. As sequences grow longer, earlier hidden states get compressed repeatedly through recurrent bottleneck steps. By the time an RNN reaches the end of a sequence, information from the first few tokens is heavily diluted. This leads to vanishing gradients and forgotten context during training. The solution they came up with is a brand new architecture called the transformer. Though, to be fair, it wasn't entirely new, since the mathematical building blocks had been there all along. They just arranged them in a way that changed everything. Transformers eliminate recurrence entirely. Instead of stepping through sequences one token at a time, self-attention allows every token to interact with each other simultaneously. We reduce sequential execution steps from O of n down to O of 1, unlocking massive GPU parallelization. Step 1 in our PyTorch pipeline is tokenization. Computers can't process raw strings directly, so we map every character in our dataset to a unique integer ID within our vocabulary. For our character-level model, we convert strings like Charizard into a tensor of integer indices. Next, those integer IDs pass through nn.embedding to map each discrete token into a continuous 512-dimensional vector space. Following standard transformer conventions, we scale these embedding vectors by the square root of D model, which is the square root of 512, or approximately 22.6. To ensure embedding magnitude align properly with the positional encodings we add next. of attention processes all tokens in parallel, the network naturally has no concept of token order or sequence position. Without positional information, a sequence and a random shuffle of its own words produce identical attention weights. We need a way to encode sequence order into our vectors. How do we teach word order without bringing back slow loops? Vaswani and the Google team used sinusoidal positioning encoding. They overlaid sine and cosine waves at different frequencies, like assigning each Pokemon in a lineup a unique coordinate tag. Each token gets a unique wave signature added directly to its embedding. Now token 0 has one signature, token 8 has another, and our model instantly knows who stands where in the sequence. It's pretty neat. Now for the core mechanism, scaled dot product attention. We project our input embeddings into 3 distinct representation spaces using linear layers. They are query, what each token is searching for; key, what features each token offers; and value, the actual information extracted when a query matches a key. To compute how relevant token A is to token B, we take the matrix product of query and transposed key. A high dot product indicates strong similarity, meaning token A should heavily attend to token B. Why do we divide dot products by the square root of d sub k? Well, in high dimensions, like d sub k equals 64, unscaled dot products grow large in magnitude. Dividing by the square root of d sub k stabilizes variance and keeps gradients healthy. Finally, we apply softmax row-wise to convert raw scores into probabilities that sum to 1. Multiplying these normalized weights by the value matrix yields a context-rich representation for every token. That's scaled dot product attention in 5 lines of PyTorch code. A single attention head can only focus on one relationship at a time. Multi-head attention solves this by splitting our 512 dimensional embeddings into 8 parallel heads, each operating in a 64-dimensional subspace. This allows the model to simultaneously track grammar, position, phonetic roots, and semantic rules. Once all 8 heads calculate attention in parallel, we concatenate their output vectors back to 512 dimensions and project them through linear layer W sub O. This unifies findings from all 8 attention heads into a single consolidated tensor. When training an autoregressive decoder to generate text character by character, tokens must not look into future positions. We enforce this using a causal mask, an upper triangular matrix filled with negative infinity. Softmax turns negative infinity values into 0% probability, ensuring each token can only look at past and present positions. Deep transformer stacks rely heavily on residual skip connections. Output equals x plus sublayer of x. Skip connections create uninterrupted gradient highways during backpropagation, preventing vanishing gradients as we stack multiple transformer blocks. Alongside residual connections, we apply end-to-end dot layer norm. Layer norm stabilizes training by standardizing feature activations across channel dimensions to mean 0 and variance 1, preventing internal covariate shift. Now we assemble the complete Porygon Transformer PyTorch class and launch training on our dataset of original 151 Pokemon names. In early epochs, loss sits above 4.0 as the model outputs random noise. But as gradients propagate, loss drops smoothly to 1.35, showing the model has mastered Pokemon phonetic patterns. We run autoregressive sampling character by character to generate new names. Flareonix, Psymander, Aquaveron, Thunderaze. With pure self-attention and zero hard-coded rules, our transformer learned how to construct valid Pokemon names from scratch. That's the power of the transformer architecture.